with Maryvonne and Maryvonne Gerin and Antoine Roueff, we try to make some concluding remarks on these meetings. I have 1 minute to do it, but I think I will be a bit late. So a few things that we have learned this week, or we have spoken this week. The first thing is that one thing that recurrently came into focus is the fact that what we see is on Earth is a 2D projection of a 3D reality. We don't have so much information along the line of sight, and there are a few way out of this. The first one is we fitting the line profiles instead of integrated brightness. Most of the time, people are trying to run their models on integrated brightness, but fitting the line profile will give you additional handles to better understand what's going on along the line of sight. And this brings to something that has been recurring also in this meeting. What is the right physical model you need in order to fit your data? The difficulty is that you don't have much data, so you want to make simple models, but making too simple models will bias your results. So you need to find the right way in between. And with the progress of radio astronomy, infrared astronomy, and so on, now we are able to observe many lines in a single run. So we should try not to think just a single line, but many lines and of multi-species, not just one species at a time. This is additional difficulty because trying to fit multi-species, you need to get some chemical assumptions or chemical model, and it's another degree of difficulty, but it will bring you more information. For instance, N2H plus is emitting from the dense core, while 12CO is emitting in the environment. So this allows you to get some information along the line of sight. And with the advent of Gaia measurements of billions of stars in the surrounding of the sun, now we are able to do some kind of 3D tomography of the ESM. So you all know about the 3D maps of the volume density of the ESM and this week we've heard about trying to measure also the unstable medium in 3D. So going from XY to XYZ. I think this is an important way to anchor our understanding of the local interstellar medium. So there have been a few things that has been physical processes that has been discussed as important this week with the idea to constrain star formation laws, and one that has been discussed twice or maybe more is where the transition from turbulence to climatic coherency is happening. This is at this point that the gravity is taking over. So this is an important point to understand why star formation efficiency is a low efficiency process. And so is it in filamentary structure this is already happened, or is it in dense core, or this is under the dense core scale? Those are open questions that people are trying to give answer in this conference. Another important thing that is happening in the field now is we start to have measurement of the magnetic field. So it's difficult. The amplitude, for the amplitude, you need Zeeman effect, or you can try to use a theory like Davy-Chandrasekhar-Fermi methods, but on the assuming turbulence of the medium and based on the line field structures. And so what has been said, I think I've seen this week a few success in this direction towards the first step of star formation or larger angular resolutions for H2 regions. What is clear is that the magnetic field is controlling, even though the electron density is not so large, the coupling between magnetic field and neutral is pretty strong, and magnetic field is controlling quite a lot into the structuration of the medium at different scale. And in particular, one thing that has been said this week is that the size of protoplanetary disk is probably related to the strength of the magnetic field. So it's not obvious to measure the field strength, but we should continue to do this. We hope that with new instruments, we will be able to do more and more Zeeman measurement, which are direct measurement of the field strength. Physics is one, but we need to do also chemistry, which is important in its own. It's important in our field because, as been said this morning, H2 is not so obvious to observe in general because he does not have a dipolar moment. And so we rely on tracer, and for those tracers, we need to understand their chemistry. Then there are other reasons why chemistry is important. It's also because this is the source of complex molecules for potentially feeding the protoplanetary disk and the protostar and the protoplanets into heavy, complex organic molecules. One thing that has been advertised this week is that dense core are chemically diverse. Their diversity is probably related to the environment in which they are located, the far UV field of the environment outside the dense core. And another thing that has been said is that we can probably draw on the chemical diversity in order to define a star formation sequence, some kind of clock of the star formation. About chemistry, one other thing that has been said is that the history of gas cells along long times is important. How it's evolved in temperature and density in order to define the final chemical state. This is not a new result, but it has been restated this time. There has been a bit of discussion about dust physical parameter, even though it was not the core of this conference. And there has been two different things that has been said. The first one is that it's not very easy to break the degeneracy between the parameter of the emissions, the beta and the temperature, but this can be done. And this can be done because there are new statistical methods of inversions, like the hierarchical Bayesian frameworks. And when this is done correctly, and when you have good dust models, you're able to try to constrain the evolution of the dust population in different environments, and you're able to what has been said is that you're able to quantitatively show the grain growth with millimeter observation. So we're really showing now that observationally that there are different kind of dust population. A large fraction of the discussion has been about how can we. So the title of the conference is unifying the views of star formation from the Milky Way to nearby galaxy. Did we succeed? Not completely, I think, this week, but I think we've made progress. So the first thing is, are Milky Way GMCs a good template for nearby galaxy? This is always a question that happens. So the first thing that can be said is that the effect of metallicity completely dominates the structure of the interstellar medium. This is one of the biggest knobs that you can turn. On the other hand, it's not completely, at least to Maryvonne, myself, and Antoine, whether it's a continuous change or whether there is a threshold in changing the properties of the interstellar medium. And this is related in particular to what has been shown about the outer galaxy. We see a gradient of metallicity, so it's not a big change of metallicity as with nearby galaxies sometimes. But does it have an impact on the structure of the interstellar medium and its chemistry? Certainly, but when this impact becomes dominant is not completely clear. Most of the observation up to now has been done in the nearby good belt clouds because it's easier. This gives better sensitivity, higher angular resolutions. And one thing that is emerging is that, at least in the good belt, we seem to see some kind of similar line intensity as a function of NH2, of the column density of H2 models. So it's not so straightforward. You need to make correction for temperature and stuff like that. But it seems that there is some common physical understanding of what's going on. And this is going in the right directions, because if you're already in the gold clouds, there was plenty of diversity. Generalizing to nearby galaxy would be difficult. This raises the question of whether the good belt clouds are good examples for what happened in the galaxy. We know that probably not completely. We know that from nearby galaxies that things are happening very differently in the bar ends or in the CMZ or the outer part of the galaxy. And I think this is already happening, but I think this will be more and more. This will happen more and more in the future. The studies that are currently done in the good belt surveys will be generalized to those environments, and this is very good because it will help us to continue to bridge the gap with nearby galaxies. There is also studies about timescales of evolution of the interstellar medium, and this is done mostly in nearby galaxy because you have an outside view, and so it's easier. And the result is that the star formation phase, the embedded star formations in giant molecular clouds, is relatively short. between 0 and 4 million years, compared to the relatively quiescent, without star formations, lifetime of molecular clouds, 10 to 30 million years. So already you see that those are relatively large range, and you can get ratios that are pretty different depending on the clouds. But one remark that has been said is that in local GMCs, in the good belt, every time that we are looking, we see in some part of them star formations. There are some exceptions, but not so much. Okay, so how do you reconcile the fact that in nearby galaxy you should have a star formation maybe 30% of the times, and the fact that locally we see star formation in more than 30% of the clouds? So maybe it's a question of definition of clouds. Maybe it's a question also of we have a static view of the stuff, and is the cloud completely destroyed, or in fact, is part of the molecules remaining? For instance, we know that H2 is difficult to build, but meaning that it's difficult to build, it also means probably that it's difficult to destroy, and it's probably not completely destroyed by stellar feedback. Is HCN a dense gas tracer? So as our colleagues, our friends of the cosmological domain would say, we have a slight tension between galactic and extragalactic people. And that we've seen again this week, even though the discussion is there for 20 years and has been renewed 10 years ago. And so let's not go into the tension, but let's try to see what have been the progress on this. The first one is that we have a problem of vocabulary. Dense gas does not mean the same for Milky Way people and probably nearby people, okay? So, and when you're making your presentation, there is a tendency to simplify and to speak about dense gas. So I think we should be, in order to resolve the controversy, we should be more accurate, okay? And start to say what we define by dense gas. I know that's difficult, but I think in order to get over this kind of controversy, we need to be more accurate. One thing that we start to see is that this is again this question of intensity of tracers versus N2H2. You see that is approximately represented by power laws, and there is a correlation between the column density and the volume density. So maybe another power law, maybe something more complex. So this means that probably you have a relationship between the intensity of ACN lines and the volume density. So I think we can all agree with this, okay? And it's probably not a step, low density, no HCN, high density, lots of HCN. So now what is pretty clear is that when you're looking in the nearby clouds, we see that a large fraction of HCN is coming from diffuse part of the clouds, and even the ratio HCN over 12CO depends, depends on the far UV illumination, okay? The question that has been raised, and that is very important, is which fraction of a molecular gas is largely far UV illuminated? And my answer, so we will try to give an answer for A and B, but my answer is probably depends in nearby galaxy of the star formation activity. If you have all of a sudden plenty of O stars, you will have more far UV elimination in the surrounding giant molecular clouds. All the more when you have embedded H2 regions. Another thing that has been said is that the ratio of the intensity of H alpha over the mass of gas in the Milky Way vary by a factor 10. So there is no such thing that a single factor. One thing that is very important, in my view, if we want to reconcile galactic and extragalactic people, is that we need to discuss about physics. The excitation of the of HCN and high dipolar moment in general molecules. The reasons why HCN historically has been said to be a dense gas tracer is because he has a high critical density. And so you need plenty of volume density of H2 in order to excite the stuff. This is true. This is true. That's clear. This is one of the possibility. But there is another one. The fact that when you have enough electrons, and not so much because you don't need so much because you have dipolar molecules with high dipole moments, you can also excite molecule with electrons. And sometimes not always, but sometimes the emission of HCN is dominated by, or at least on par by the electrons. All the more you are in PDR regions far UV limited because you have more electrons. Okay? Or in diffuse gas, because then you have less UV, but you have less absorption due to high ionization fractions due to the far UV is going further away in diffuse gas. Another thing that is clear also that this is going from the other end, nearby galaxy. We have trends with between lines, power law trends over order of magnitudes between HCN or HCN over 12 CO and the star formation efficiency. So we need to understand those. And the question I would like to ask is, at one point, when the angular resolution you have in nearby galaxy is much more limited than what we have in the Milky Way, obviously. And so at one point, do you start to count the number of clouds you have in your beam instead of trying to probe the proportion of dense gas or the physics, okay? At some point, the beam is so large that you're counting more than, you're making a statistical average. So HCN is one, but then what are the alternatives? I would say that probably the CS, SO, CO molecules have behavior that are similar to HCN. We have exceptions like N2H+, but this week there has been also some discussion about other tracers. So first one has been H2 lines. That is the dominant by far molecule in the molecular gas, and those ones are difficult to observe, but they have plenty of degree of freedom, and this can be used to make powerful physical diagnostic. This morning, we think that you can try to constrain the ionization, the cosmic ray ionization rate. Another thing that has been a bit exotic this week, but it's important, is people are trying to on dense gas. The gas is making ices around grains, and this makes a lot of chemistry and so on. Very important for comets and for protoplanetary disk. And so with GWST observations, there is a generalization of the measurement of the ices compositions. And with the advent of MERCAT and the future SK, what is clear is that the use of H1 will be more and more used to study the transitions between H1 and H2 phase. And why is this? It's not because it was not important before, but with SK and Meerkat, you increase quite a lot the sensitivity and thus the resolution. So you will be on par between molecular gas, maybe not, but molecular resolution and H1 resolution. Even though we are making large progress in our instrument, we still have a gap in resolutions. Nearby galaxy right now are measured at best on 10 parsec scales resolutions, most often at 100 parsec scale resolutions, while the largest clouds that we can measure in our galaxy are 10, 20, maybe 100 parsec for stuff that are further away from the sun. And so we still have a question of what to do with all the nice nearby observations at limited resolutions in order to constrain the processes of star formation that happen inside the beam. One possibility has been to propose this week is to try to model the sub-beam PDF of the column density of H2 and trade off the fact that we have many different lines observation in nearby galaxy. Not so many examples, but again, a few years ago we had one, now we have 10. In a decade we have 100 and so on. So this will become more common to have plenty of different lines, and we can use this to try to constrain with empirical model of the line emission for local GMCs to constrain the sub-beam PDF. This is related to whether our local clouds are good template. And so whether we can do this in other parts of the galaxy. This conference was also about data science. This is related to the fact that there is a boom in the quantity of data we are getting today. And so it has been said several times this week that we have huge data sets. Huge not only in space, millions of pixels, okay, but also in spectral dimension. Good resolutions, plenty of lines, okay? Today, our data set, 1 million pixels, 1 million frequencies. There are not so many data sets, but tomorrow there will be plenty, okay? So we need to do stuff like this. It's been said that when you have such data, we cannot just naively apply the method that has been developed in data science, for instance, on Earth remote sensing, to the case of astrophysics images. Why is this? It's because the edges, we don't have, this has been said yesterday, we don't have here, if I'm taking a picture of this amphitheater, I will see plenty of very strong edges. This is not the case in astrophysics. The edges are, well, it may be the case for planets, but most often, in most of our observations, we have fuzzy edges. The other stuff that is happening, we have varying signal to noise ratio. When the optical thickness is not so large, you may have several components along the line of sight. So we can't use a method off the shelf. We have to discuss with data scientists how to adapt their powerful methods to our own needs. And that's why we made sure this week to have some people from this community to present their work to get this discussion started. So we did this, we started this in the DAOISM's grant 6-7 years ago. It takes time because we need to understand each other, but when I hope that the stuff we have been able to deliver in the DAOISM grant show you that in the end, it pays off. In order to pay off, you need a prioris. It's never free lunch, okay? And the a prioris can be of two different things. You can be a prioris on astrophysics. We should not have too many a prioris on astrophysics because this can turn very quickly on bias. Another possibility is to have a prioris of noise. This has been discussed yesterday. But then it means that we need to have a good knowledge of our detectors, okay? And to improve our simulator of the detectors. From data science, there are many methods, and a few ones that have emerged this week, and probably we are missing others. From the few ones that emerged this week, the first one is information theory, which is powerful because it can tell you, it can help you to measure nonlinear correlations. So it seems a bit abstract, but it can tell you how to measure nonlinear correlations that often happen in astrophysics in a very generic frameworks, okay? To know whether there is an actual correlation without depending on the method to fit it, okay? So, for instance, is one line sensitive to a given physical parameters? In general, in astrophysics, we are fitting correlations, but the information theory gives you tools to do this without any methods of fit or stuff like that. Another thing that information theory gives you is it enables you to measure the amount of information you can extract from a data set. Okay, it give you a lower bound of the variance of your physical parameters. And this is important because if you have an estimator that gives you on the error bars this lower bound, you know that you can stop. There is you won't extract more information from this data set. Fusion has been discussed a couple of times in order to. So we've seen that we want to go more and more to spectral data cubes. But our instruments like GWST and future ones sometimes give you very good spectral resolution, sometimes give you very good spatial resolution. And it's rare that you get both together. And the question of fusion is to try to make a few assumptions and to take the best of both worlds to make cubes. Bayesian approaches are very important in inverse problem. And this is something that is very well recognized in the astrophysics community, but in the ESM community today. So we've been speaking about hierarchical models. We've seen that one thing that is happening in data science is that we have much better sampling methods today, much more efficient, that are able to go from in the space of parameters to go from local exploration of your stuff to global ones to see whether you have multi-mode and so on, which multi-mode means that you can have some ambiguity in the parameters. And this is very important for us to know whether there are ambiguities. The use of generative models has been discussed several times. Be it neural network or scattering transforms, and this is very important the important part is that those generative models right now will be able to be learned on the data itself. Okay, it won't be models that we will deduce from laws, but it will be learned by the data itself. And this is important to, for instance, cosmic microwave background, but also in our domains to do deconvolution, for instance. Several times the autoencoder word has been used. This is important when most of machine learning today is done, large fraction is done in supervised learning. Okay, you have a data set that is tagged, and you're using it to learn something and to apply it to the same conditions. In astrophysics, we don't have so much tagged data sets. And in order to avoid this, you can try to use self-supervised, which are using autoencoders. So neural networks are used in spectroscopic studies of the SMs to do model emulator, model in this sense, physical and chemical models that are low, intrinsically low because there are plenty of physics and chemistry, so it's difficult to solve them. And so you're making grids, and then you're making an emulator, and then you're able to do very fast inversion, Bayesian inversion search of the parameters. In the big data cube that we will get with SK, when you're searching for exoplanets, all those, a large fraction of the astrophysical discovery is coming at low signal-to-noise ratio. And so it's important to have automatic methods to do this. And it's a bit like trying to find a needle in a haystack. And we see that neural networks are very powerful at doing this. And we've seen also that when you have plenty of complex land surveys for odd corinos, for odd cores, and so on, you can't hire 1,000 students. You only have one, so you need to help him to do 1,000 lines, the analysis of 1,000 line survey, and so we need machine learning. Final remark. This is just the beginning. In the making, for instance, I will speak what I know most, millimeter and submillimeter wavelengths domain. For instance, at IRAM, we are developing at the 30-meter telescopes, we are developing a camera, a multi-beam camera, that will have 49 1mm pixels and 25 3mm pixels. So everything will not happen in 2030, but the first one around 2030 should be this. Maybe I'm a bit optimistic because there are challenges in doing those instruments, but the community at large is going into this direction of making cameras in the millimeter. So right now, I remind you that we have 1 pixel at the 30-meter. So all the results you've seen from the 30-meter are coming from 1 pixel. All of a sudden, we'll have 50, so 50 times more data. Okay. ALMA WSU is a different way of doing this, but it will increase the number of channels, basically, going up to 1.2 million of channels in a single observation. It will take a bit longer. It should be ready around 2035, completely finished. Probably part of it will come earlier. So this means that I just want to give you a number, 2. For the Alhambra instruments, we will get of the order of 3 petabytes per year of data around 2030. For ALMA WSU, we will have 17 petabytes of data. Okay, this is much less than what is said to be for SK, but still, those are big numbers. Okay, so let's be prepared to do plenty of very nice science with those, but then this will ask us to make an effort to work together with the data science community to apply their powerful algorithms. I'm done for the science final remark of this conference. I want to finish with a few acknowledgements. So first, institutional acknowledgement. We are here at IAP in this nice amphitheater. We didn't pay for it. So thanks to IAP for this. We have contributions to the organizing fees from Observatoire de Paris, that is just nearby. We also going at the canteen of Observatoire de Paris. Let's first acknowledge also the DAOISM grants from the ANR, Agence Nationale de la Recherche in France, that has funded most of the cost for this week. The lunch, the coffee break, some of you could come with these funds. Then organizing such a conference also requires peoples behind them. So the LOC and the scientific organizing committee. So I would like to thank, I will probably forget people, but I see Emeric, Frank, Antoine, Maryvonne. I would like to thank people that are not here because they could not make it for very good reasons. In particular, our statistician colleagues, so Jocelyn Chanusso and Pierre Chenet, who used their connections to ensure that we could have talks about data scientists. It's not always easy to interest data scientists to our domain, so thanks to them. Did I forget somebody from the... I don't think so. And then thanks to our young colleagues that helping us in the DAOism, so Yann, Myriam, Elena, and others that I forget. Do I forget something? I think that's almost all. So let's thank everybody, and I hope that conference like this will reiterate in the future.